Welcome to Cruise in the Cosmos. I am Joshua Laughlin.
And I'm Jason.
Tonight's episode, we're going to talk about stars, specifically the sun.
Aren't those different things?
No, Jason, the sun's a star.
Are you sure? This guy doesn't seem to think so.
Well, that guy's obviously wrong. The sun's a star.
I don't know. I mean, if two people...
Wow, okay, so a lot of people seem to be uneducated about stars and the sun, but the sun is a star.
No, I mean, you can't be wrong if three people...
Okay, look, the sun is a star. It's our star. It's the sun. The sun's a star. The sun's a star! Ugh! Alright, so we're going to talk about the sun, which is a star. Alright?
Okay.
Okay. So, let's start with stellar evolution.
The birth of stars.
That's right. So let's say you're looking at the Orion constellation. It's easy to find. It's in the northern hemisphere. In the Orion constellation is the Orion Nebula. If for anyone that's wanting to find it, you look for the three dots for the Orion's belt. Right below that, small three dots. In the center is a faint fuzzy dot. And that would be the Orion Nebula. Very well studied. It's 1,500 light years away.
Right. And molecular clouds like the Orion are mostly made of hydrogen and helium, with a little bit of heavier elements from previous generation of stars.
That's right, Jason. And molecular clouds are cool enough on the inside to allow hydrogen to form as well as complicated elements, like ethyl alcohol.
Booze.
Space booze.
Huh.
Nice.
Tequila.
Well, no, not tequila. No, sorry. But clouds are massive enough for the force of their own gravity to make them collapse in on themselves and eventually form stars.
Well, that's right. We don't know exactly how this happens, but more or less it's like this. At first, the molecular cloud is so light that the gravity really doesn't affect it. Eventually, though, gravity will take hold of the particles and force the cloud to collapse in on itself. This can be triggered by the shock wave of a supernova, more than likely. Usually, once this happens, the density of the cloud will increase, and so will the gravity, causing it to actually form off of the rest of the cloud.
This eventually will lead to the stars and planetary systems. A star that's the mass of, our sun takes roughly about 10 million years to form. Whereas stars with a mass, let's say 11 times our sun, takes only about 100,000 years. And that's because larger stars, they form quickly, they burn up all their energy quickly, and they die quickly.
Ooh.
The sun.
Wow.
Oh yeah?
Yeah.
Look at this. Yeah.
What other wizardry do you have?
Well, I have this. Soho videos.
Soho videos?
Soho videos.
Nice.
Indeed.
Let's see what's inside.
You mean the core?
The core.
The core. So in the core, it's very hot. It's dense. 15 million degrees Kelvin. It's so hot it destroys the internal structure of the atoms. It splits them. Protons and electrons remain and drive the reaction. They create a neutral material. It makes up the core, and it's called plasma.
Right, the hot temperature causes them to move quickly and slam into each other. This releases energy, and it's the source of the sun's power.
Well, that's right, Jason. I'm actually really surprised. Give us some good information here. What else you got there?
Well, Josh, I guess the next zone we'll hit is the radiation zone. So radiation is the most effective way to transfer energy. This zone is actually a little bit cooler than the core, and that allows atoms to remain intact, which is very important. It's only about 5 million degrees Kelvin. Only. Energy generated in the core is actually passed along from atom to atom here.
That's right. Actually, the energy is randomly passed. It could take over 170,000 years for the energy released in the core to escape the radiation zone. That's the photon in the center of the core, making its way just to escape the radiation zone.
Right, and once it escapes the radiation zone, it actually makes its way to the convection zone. Once out of the radiation zone, the energy actually uses a new transport mechanism. This new method is required because the area is a lot cooler. This time it's only 2 million degrees Kelvin. Atoms absorb energy here, slowing the travel of energy. The atoms move with convection.
Well, I guess that's why they call it the convection zone.
Astute observation.
Well, that's the hot material moves on the top. The cooler material moves on the bottom. Just like boiling water.
All right.
Hot material follows a direct path, and it may take only a week to exit the zone.
Well, once it exits, it actually meets our first visible region, the photosphere. So the photosphere is actually our first visible region. The gas is so dense here that you can't see through it. Someone maybe consider it a surface of the sun. You can actually see evidence here with the convection zone on the surface with the rising and falling of the hot and cool bubbles. This is called granulation.
That's nice. It's actually very accurate, Jason. The energy here is transported once again by radiation.
Right. And it is a little bit cooler. It's 5,800 degrees Kelvin. The gas is so thin that the atoms absorb and release the energy.
Well, Jason, I also have something very interesting, something you could see through a telescope. So, Jason, when you're looking through a solar telescope, or say you get a telescope with a solar filter,
Okay.
and you're wanting to look at the sun, and you might notice some black spots on the surface.
That sounds a little odd.
Not really, Jason. These ever-changing black spots are sunspots.
That makes sense.
It does. And in fact, though they're dark in color, they're actually very hot.
That's right. The photosphere that we talked about actually has a temperature of 5,800 degrees Kelvin, as I mentioned before. But a typical sunspot has a temperature of about 3,500 degrees Kelvin.
Well, the inner part of the sunspot is very dark, and that's known as the umbra, whereas the lighter surrounding area is known as the penumbra.
Show me what that looks like.
It looks like, well, this.
And now I guess that leads us to another region called the chromosphere. Now the chromosphere is above the photosphere. It's about 2,000 kilometers thick. Energy here is still transported by radiation, and it's about 20,000 degrees Kelvin. Good enough for an ocean and a vacation. Hydrogen atoms absorb energy here and emit a red light.
Well, that's right, Jason. The chromosphere is an exciting and unique feature of the solar landscape. So, astronomers have found many exotic structures, such as prominences.
Prominences?
Exactly. And what a prominence is basically a hot gas loop. It's an arc, and it reaches into the chromosphere and often extends into the corona.
That's right. Some of them actually have the width the size of Earth and may approach about half the diameter of the sun itself. Prominences are often associated with sunspots.
Okay, Jason, I do enjoy this video. But after the whole fiasco earlier, I really don't think you should be all snapping all willy-nilly like. I mean,
Closely related to prominence are large energetic coronal mass ejections and flares. these CMEs begin as a loop that explodes and spews all sorts of solar material into space, including some strong X-rays and some ultraviolet rays.
That's right, Jason. For example, if let's say one was heading right towards us, let's say the radiation will arrive at Earth in about 8 minutes. It will severely disrupt the ionization of Earth's upper atmosphere. This can cause major problems with communications and power systems everywhere. So let's say 24 minutes later, the next wave hits. This consists of very high energy protons that can be extremely harmful to astronauts in its way. Oh, you think we're done? No, we're not done. So, after about 1 or 2 days, the Earth is slammed again, with a magnetic shockwave traveling at more than 600 miles per second.
What does that do?
It does stuff.
Auroras.
Indeed. The aurora. When charged particles hit our magnetosphere, they go up and into the pole and creates the aurora borealis.
Pretty.
Very pretty.
So that was a pretty cool picture. Did you know back in 1989, one of the strongest flares ever observed erupted, causing a power failure all the way down in Quebec? And that created an aurora borealis all the way down to Key West, Florida.
Nice.
Now, these powers that you see on me and the flares cannot be overestimated. Flare temperatures may reach about 50 million degrees, which is several times hotter than the core of the sun. The power of a single CME flare, if harnessed, could actually meet the energy needs of the Earth for millions of years.
Well, Jason, that's a lot of good information.
Well, thanks. Well, that's a very good transition. And speaking of transition, that leads us to the next region, which is the transition region. The transition region is actually a very thin layer. It's only about 100 kilometers thick. The temperatures, though, will raise to well over 2 million degrees Kelvin. We actually don't know why it raises so high, but we figure it's from the sun's magnetic field.
That's right, Jason. And that brings us to the corona.
More ethyl alcohol?
No, Jason. It's the outermost layer. It's very thin. It's very faint. It stretches far out into space. Its particles reach Earth's orbit. These particles are known as the solar winds. They have many different lengths of energy, from radio to X-ray. Well, Jason, I'm actually very impressed.
Thank you.
This is one of my favorite subjects.
I know that.
You've done your homework, it looks like.
I have, actually.
Well, tell me, how do stars live their lives?
Well, Josh, the sun wakes up and puts on its pants one leg at a time, just like any other star does.
I spoke too soon. Moving on. So, let's say stars with a mass of 0.8 to 11 times the mass of our sun, they have very similar lives. Our sun is about 4.5 billion years old. How do we know this? Well, because we can measure the isotope ratio of various elements.
Boom.
So, the sun has been converting hydrogen to helium all this time, all these years. It's converted roughly about half of its hydrogen in its core so far. It's 30% brighter than it was when it formed, and it will continue to get brighter and grow.
Right, in about 3 billion years, this thing will actually evaporate all of Earth's oceans. And in about 5 billion years, fusion will actually stop.
So, gravity will compress the core and will form carbon and oxygen. Now, while the core is being compressed, the outer layers will expand and it will form a red giant. So, red giant. It may extend to Earth's orbit.
Obliterating all life on Earth.
Well, I mean, we don't...
Obliterate!
Okay, gloomy Gus over here. The helium fusion will stop in the center of the sun. But it will continue in a shell. Itself surrounded by a secondary hydrogen fusion shell.
That's right, and this will actually make it more luminous and brighter, as well as actually more unstable. This will also bring more carbon and oxygen from the core to the surface. Soon after all this, the nuclear reaction will cease, and the surface of the sun will actually expand from a few light hours to 2 or 3 light years.
That's right, Jason, and this is known as a planetary nebula. So, the core will be visible for the first time because of the low density of the gas. This dead star will be no bigger than Earth. It will contain almost half the mass of the sun.
Wow.
And it have a temperature of about 30,000 Kelvin.
30,000 what?
Kelvin.
That's a lot of people.
Degrees Kelvin. Not people. It's temperature.
Huh.
So in 10,000s of years, the gas will fade away and leave what is known as a white dwarf. Now, what planets are left behind will continue to orbit.
Right, and that's estimated to last about 9 billion years, and during that time it's still going to be cooling and fading in brightness. Actually, some of the oldest white dwarfs that we found are about as old as the universe itself, at least twice the age of the Earth, and those things still reach temperatures of 4,000 degrees Kelvin.
That's right, Jason. Some interesting things to note that we believe that in the center of white dwarfs is a giant diamond.
Ladies.
Also, the only reason the white dwarf is really glowing is because it's the residual heat that was left over from the sun. At this point, the star's dead. And eventually, we believe it's going to become a black dwarf.
So that seems like it might be kind of hard to see.
Well, it's not radiating any light.
So what you're saying is that whenever I'm cruising around in my intergalactic spaceship that travels at light speed, and I might run into one of these, kind of like a parked car. I'm not really sure if my insurance company's going to like that.
Yeah, we're going to go with that, Jason.
News of science fact.
So, news. We had some interesting things going on last time we recorded. For example, the solar magnetic field is going to be flipping.
Doom and gloom.
No, none of that. It's actually very normal. It happens every 11 years. It marks the midpoint of the solar maximum. We don't really know why it happens. It just does. What's going to happen is the field's going to weaken, go to zero, then emerge again with opposite polarity.
Whatever works, I guess.
Yeah, it could cause some minor notices on Earth, just because of the way the sheet is that the heliosphere and all its protectiveness. It could cause some weird turbulences, but for the most part, we're just gonna be fine. It's very normal. If you've never heard of it, well, you've obviously lived through it.
Yeah, I think what last time it happened was it 2001 or 2, somewhere around there?
Somewhere around there. I mean, like I said, it happens every 11 years, and this is getting ready to happen anywhere from 3 to 4 months. Another interesting news article is the Icarus Interstellar Starship Congress. This is going to be taking place on August 15th through the 18th.
Okay.
Something interesting is they're going to be awarding a prize for a new design, for spaceship design, or an improvement. Their goal is interstellar travel by the year 2100.
That's not that far away.
Not that far away. They have a lot of cool. It's really nifty when you really get down to it. I really advise anyone that's interested, especially engineers, or anyone that's a physicist, any scientist, or anyone that really is interested in interstellar travel, take a look at their website.
Absolutely.
Definitely should attend the conference if you can. Alright, so lastly, we have the Perseid meteor shower. It's going to be taking place this weekend, from today, which is the 10th, through the 13th. I suggest anyone that really wants to look into the sky and never seen a meteor shower, take a look.
This is actually supposed to be one of the best ones of the year. It should have the most frequent amount of meteors, and I'm excited.
I'm excited as well. I know a lot of people have been asking me about this, and we wanted to make sure that they got the word out. If you have an idea where to look, definitely try north, south, east area. You could use compasses to help you find where these directions are as things rise and set. But they should be easy to find. Dark sky is very, very suggested. And this is going to be, like you said, one of the brightest ones of the year.
Absolutely.
Next time on Cruising the Cosmos.
We're going to talk about big, hard balls.
They're planets, Jason. Are you recording? Jason, I got the whole world in my hands.
Red Giant!
No!